Ladies and gentlemen, my name is Kunguang. I'm from the DIKWP research group of Hainan University. It's an honor to present my paper now. My paper title is Computer Architecture and Chip Design for DIKWP Artificial Consciousness. So my presentation contains divided to 5 sections. The first section is introduction. In striving for thinking and behavior consistent artificial intelligence system, our proposed model, an artificial consciousness system, integrate concepts of from DIKWP and the consciousness theory, offering the world's first mathematical definition of AC, implementing this within the DIKWP computer architecture. DIKWP language and the runtime environment aims to surmount programming complexities, establishing the groundwork for a DIKWP software hardware ecosystem. This DIKWP-based architecture or DIKWP guaranteeing efficiency, controllability, and the semantic concurrence between human-machine interactions, minimizing semantic loss. Here is a related work. The first related was an hardwareization of software. Hardwareization of software refers to the process of transforming software functionalities into hardware for implementation, which accelerates from processing speed within specific domain while maintain lower power consumption. For instance, contemporary AI acceleration chip and their architecture, which chips lack good versatility. Once outside a specific domain, they become unusable, thus being limited to specific software or tasks. The next related work is computer architecture. So as we know, the von Neumann architecture is capable of adopting a stored program concepts, enabling computer to execute a variety of tasks. Its process generality being applicable to solve device computational problems, and allows for flexible programming and configuration based on different requirements. Now, but von Neumann architecture was built for Turing computation, but it exhibits limited compatibilities in handling non-computational issues, such as direct natural language processing and knowledge learning inference. The third rate was about the DIKWP. So our artificial consciousness, the theory based on existing DIKWP-related theories and the related work on DIKWP cognitive interaction and content conversions. We propose to combine human cognitive modeling with DIKWP theory to construct an artificial consciousness system so that the artificial consciousness system has the characteristics of thinking and behavior consistence. The third section is problem description. The problem description divides the two parts. We can initiate a discussion by delving into the potential challenges associated with the DIKWP financial systems. The system comprises the three layers: the application layer, and the support layer, and the storage layer. Assuming the necessity to implement a risk control subsystem based on DIKWP artificial consciousness related theory, as indicated on the right-hand side, we will encounter the following challenges. The first challenge is challenge of traditional programming language. The left table is our evaluation result. The y-axis represents the elements of DIKWP input, while the x-axis corresponds to the target type elements for DIKWP conversion. We have defined a trend PDCCIU to represent results of an evaluation conducted during the development of AC system for the programming difficulty PD, computational complexity CC, and the input uncertainty IU, except as implemented using high-level programming languages. So, the evaluation metrics for PD encompass three levels: easy, moderate, and difficult, as follows. The second element is CC, which is evaluation metrics for CC compass three categories is low, medium, and high. The IU represents a set of uncertainty in the input DIKWP elements, with elements furthering characteristic of incompleteness, inconsistency, and imprecision. So we can find the W2, W2P, or P2W, and P2P is difficulty higher and include ICP, ICS, and IPI. The second challenge is hardwareization of software. As we know, if we want to accelerate our software function extremely fast, we must design chip and the development a lot of software function into the hardware. So among the challenges associated with software-hardware integration, the most significant are manufacturing cost and adaptability. Manufacturing cost primarily entail economy considerations regarding software-hardware integrations. Due to the high development cost of hardware and the limited application scenarios, this situation can lead to elevated cost opposed to each chip. In terms of adaptability, hardware-based systems struggle to adapt to future technological changes. As technology advances, new hardware design may quickly become obsoleted, whereas software is often more amenable to accommodate these changes. Therefore, we need to construct an integrated software-hardware platform to enhance its applicability, thereby reducing the opposition cost. The third challenges is traditional computer architectures. The von Neumann architecture relies on performance of CPU, which in turn is dependent on the performance of memory. Memory often poses a bottleneck due to its comparatively restricted speed, which is named the von Neumann bottleneck. Von Neumann architecture computer were conceived for Turing computation, which has reached notable speed and precision in numerical processing. In reality, many phenomena are inherently ambiguous and challenging to express precisely using numerical calculations. The next challenge is about the DIKWP on natural language processing. The first is no unified paradigm for conversion about DIKWP content driven by purpose. The second is failing to represent semantic variations about the DIKWP conversions. The third is how the DIKWP model interacts with humans, which meaning the DIKWP model how to reconstruct to the natural language for humans. For the research challenges, we want to change the challenges into the engineering issues to overcome. So the next section is architecture design. The left side is we propose the DIKWP architecture. The first part is the DIKWP computer architecture. The blue arrow is the DIKWP control string. The black arrow is DIKWP semantic string. It's different from the data string, just like the traditional computer architecture. The next is the DIKWP runtime environment. The DIKWP runtime environment include the DIKWP interpreter, DIKWP semantic encoder and decoder, which not only act as a bridge for software and hardware, but also human and machine. To address the challenges in processing knowledge, wisdom, and purpose using traditional programming languages, we propose the DIKWP language as a domain-specific language. It is designed for human-computer interaction within the DIKWP architecture. So as the left tables about the DIKWP language, the grammar. To ensure that DIKWP language can be interpreted for corresponding instructions in downstream tasks, we keep the keywords as the left tables. The next part is the DIKWP hardware relation of software. As the right figures, the PPU, DPU, IPU, KPU, WPU corresponding the purpose processing, data processing, information processing, knowledge processing, and wisdom processing, respectively. They are controlled by DIKWP control units. The DIKWP control unit, we're using the FSM finite state machine to represent its state. So we divide S0 and S1, S2, S3, S4, S5, and S6 to present the different statements. The uncertainty processing unit. Regarding the processing of uncertainty, we need to model it based on human reaction on natural language content. We abstract human language processing into levels, one being the second single system processing based on conditional reflex, represented by the arc lines in the right fingers, which we define as surface level processing. We define the process of direct reflection as a function, denoted as FCF DIKWP-CT, which represents the corresponding results of mapping DIKWPs directly to the cognitive and the semantic space. Another factor is that due to the input language being incomplete, inconsistent, or imprecise, specific reflection don't form at the surface, or multiple reflections occurs, meaning including empty set or set contain multiple DIKWP elements, just like this equation. Based on the after mentioned equation, we define the source function T DIKWP1, which encompasses the two processing steps. So the last unit is a security control unit. The security control unit we call the SCU primarily handle whether the output of the transformation processing under the influence of purpose fulfill its security purpose, just a right algorithm. The last section is conclusion. Our study, based on DIKWP AC theory, examines current constraints in complementing DIKWP AC systems and propose the integrated DIKWP chip and hardware architecture, introducing DIKWP language, runtime environment, and microarchitecture within the chip. We aim to create an ecosystem facilitating DIKWP's implementation, bridging cognitive gaps in human-computer interaction, and improving system accessibility, reliability, and efficiency. That's all. Thank you.